I've seen videos by people that have made their own EPROM programmer, but most seem to involve a PC and a USB connected device. However, this is a real homemade EPROM programmer. As a young man, after I'd learned about microprocessors at college, I realised they would be involved in nearly all aspects of electronics in the future. Learning theory is one thing, putting it into practice is another. I needed to give myself experience of designing complex electronic projects involving most aspects of electronics. So I planned one involving radio frequency and audio frequency analog electronics, interfaced and controlled by microprocessor-based digital circuitry. Back in 1990, I planned my project. It quickly became apparent I would need an EPROM programmer to program and store the software I planned to write. However, EPROM programmers were very expensive and required a PC. As I had neither and had very little money, I had no choice but to design and build my own EPROM programmer. So here it is. I recently found it buried in a drawer of old junk, but after giving it a new set of switches, I was surprised to find it to be fully functional. Not bad for a 30-year-old device that was only intended to be a quick means to an end. Here we have a multiplexed hexadecimal display that's driven by a character set ROM chip, which from memory is an 82S123 TTL bipolar fuse-blown device, so the memory is permanent and very resistant to static damage, hence why it's still working after 30 years. I had to program that in a breadboard using dip switches. The green digits show the 16-bit address bus that can address a whopping 64K bytes of memory. The red digits represent the 8-bit data bus. The internal RAM's memory address is selected by the green count up and count down buttons. The data value is set by these red buttons. So, in program mode, let's read the data value at address 0. We press read and it shows we have FF in the RAM. Now let's write a new value to that address. We select a value, then press write to write it into RAM. And now it reads that value when we press read. Now let's do the same to the next few addresses. So that's how the internal RAM is programmed. To verify what's been written, we select Output Mode and scroll through each address. Yes, I know what you're thinking, and you're right. It's the main drawback of a PC not being involved. Writing, programming and editing a software program becomes a laborious and time-consuming task. There's up to 64,000 8-bit hexadecimal data values that need to be individually programmed and verified. So, where does the EPROM enter the equation, you may ask? Well, it's with this module. Different modules will be required for different EPROM chips of different memory sizes. This one happens to be designed for the 27C64 and the 27C128 EPROMs. Also, the 28C64 EEPROM. Please note that this flush slider switch is set to unload as opposed to program. It's recessed and out of the way, so it can't be accidentally knocked into the wrong mode when handled. 12.5 volts is required for the EPROM programmer voltage pin. On the back we have a 37-way D-type connector. Above we have a 28-pin zero insertion full socket for the memory chips. So let's insert our first chip, the 28C64 EEPROM. Plug in the module and power it up. Let's see what's in the chip by selecting the run mode and scrolling through the addresses. It seems we have all zeros. So, to program the EEPROM, we need to change the programmer module's slider switch from unload to program, to change the data direction and programming connections. Then select the clock speed for the correct programming pulse widths. We also need to change the programmer's mode to run. Then we select Go on the programming module. Now it's programming. That will do. To verify the programming and to read the EEPROM, we need to change the programmer's module slider switch from program back to unload. Then we need to change the programmer's mode to run. We can scroll through each address to confirm that the data has been written correctly. Once you have a full software program written into an EPROM, you can read the whole lot back into RAM to debug and edit it, and then program another EPROM or rewrite an EEPROM. This is an interesting experiment. This EPROM was programmed about 23 years ago. There were varying opinions back in the day regarding data retention times. Some said 10 years, others said 15 to 20 years. So let's see. As we are only reading the EPROM, I'll increase the clock speed and switch Go to unload the ROM into RAM. That will do. To verify what's been written into RAM, we select the output mode and scroll through each address. Oh, there's no data loss there. F3. I remember that command. It's disable interrupts on a Z80 microprocessor. What's next? Oh, C3. From what I remember, that's an unconditional jump. The following 2 bytes should be memory location. 0D01. I think the first byte is the least significant and the second byte is the most significant. So let's go to address 01, 0D to have a look. ED. I vaguely remember that being an individual bit function, but I can't tell you the precise operation. I guess this was the initialization subroutine, like a BIOS, before it jumped to my primitive operating system, where interrupts would be enabled. Well, it seems like the 20-year data retention advice was the most valid, as it appears nothing has been lost. This was a nice trip down memory lane. Thank you for watching.